Hello, welcome back to Piers Rocks. Ever have one of those days where you feel like everything's going backwards? In the last episode, I repaired some problems that I think I caused to this 2040 disk drive. This time, I need to take another look at my 2031, because while I was fixing this 2040, my 2031 failed. We've seen this 2031 on the channel before. In fact, most of its insides were 1541. I think back in the day, whoever owned this disk drive decided to convert it from a 2031 to 1541 by just replacing the main PCB. I've now reverted it to a 2031 with the addition of some additional circuitry, but also to get it working I had to rewind the tachometer coil on the drive mechanism. Now, while I was repairing the 2040 disk drive in the last episode, I accidentally left this 2031 on all night. It felt fairly warm when I noticed, so I turned it off. Then, when I turned it back on, it would no longer work. So here's the symptoms. It turns on, the motor continuously spins, and the red light blinks on and off. Now, there's two possibilities here. One is that this is a flash code from the CPU, so the CPU is partially booting and finding a fault and giving me a single flash as an error code, in which case there's a problem with 0 page. Or the other possibility is that the CPU is just continually on a reboot cycle, so it's booting, turning the red light off, and then immediately rebooting, the red light is coming back on. We'll take a look at the schematics and go through the theory of this drive in a second, but I just wanted to revisit the internals of this disk drive. So it's a stock 1541 PCB. So it's got a 6502, it's got the ROMs here and the static RAM here. Now the ROMs I've replaced with the 2031 ROMs, and then the first 6522 is actually inserted in a daughter board that has all of the IEEE 488 circuitry on it. This is the thing that actually converts this disk drive back into being a 2031. Now, for most of the diagnosis and fixing of this disk drive, I'm actually going to do it without this daughter board in place. Right now the CPU I don't think is getting anywhere near far enough to try and talk to a 6522, so I don't imagine that that's our problem, and having the daughter board out gives me a bit more access to the circuit board. Now I think the main circuitry that we're going to be looking at in this repair is the 6502 itself. The ROMs, I suspect the CPU isn't getting far enough to even talk to the ROMs right now, but the static RAM is going to be suspect, given I think I'm getting a 0 page flash code, and also this 74LS42 chip here is involved in accessing the static RAM and the 6522s on this device. Now, in case you're wondering what 0 page is, 0 page is the first 256 bytes of memory on a 6502 powered device, and on this disk drive that is provided by the static RAM here, but access to the static RAM, as I said, is controlled by this 74LS42. So without even looking at the schematics, which we'll do in a second, main culprits for me are likely to be 6502, that 74LS42, and the static RAM chip. So let's take a look at the schematic. So this is the schematic for the 1541, and of course we're looking at a 1541 board here, although the 2031 schematic is very, very similar. On the left hand side we've got the processor, the 6502. Then we have the 2364s, these are the two ROMs on the disk drive, and then we've got UB2, which is the 2016 static RAM. And the 74LS42 I pointed to before is this chip here. So I'll explain what's going on. Essentially, the 6502 has to be able to select between talking to different devices on the internal bus, and the devices it's talking to are the ROMs, the RAM, and the 6522s, which we can see over on the right hand side in this schematic, but those aren't really relevant for our discussion. And it's using address lines A10, A11, A12 and A15 to go into this 74LS42 chip. This is a decimal decoder chip, so it's essentially taking whatever number is provided on A, B, C and D in binary and converting that through into pulling low one of the output pins, which are numbered 0 through 9. So if 0 comes in through A, B, C and D, then it will pull pin labelled 0 low. That's essentially how it's selecting between the static RAM and the 6522s. It's then also using A15 and A13 using this circuitry here with a bunch of logic gates to switch between the different ROM chips. Now I suspect this is a bit of the circuit that we need to be concerned about, because we're getting, I think, a 0-page error from the disk drive, which suggests to me that it's either unable to properly talk to the 2016 through this circuitry, or the 2016 itself is bad. So what I'm going to do is get the oscilloscope out, and we'll start at the left hand side here and we'll probe the 6502 and make sure that the 6502 looks like it's operating properly, and then we'll step through the circuit. We'll look at the 74LS42, and then we'll look at the 74LS00 and 04, and then look at what's going into the static RAM and how the static RAM chip is behaving. So I have the drive on and it's exhibiting the same behavior. I've unplugged the motor so we don't hear the motor spinning around. First of all, I'll check the CPU ready line. So that's going high, which is what we'd expect to see. One of the clock lines, that looks good. I'll just change the time base. There we go, it looks like we're getting a decent clock, 1 megahertz, that's what we expect to see. The IRQ line is high, which means it's not active, so it's not being interrupted, which is good. 5 is not connected, 6 is NMI, non-maskable interrupt. Again, we want to see this high, and it is high. Sync, VCC, we're seeing high, obviously, and then we're onto the address lines. And we're seeing activity on address line 0, and address line 1, address line 2, address line 3. Address line 4 is just high. If the CPU is just trying to access the 0 page, then we wouldn't really expect to see much activity on the rest of these pins. We'll take a look at pin A10, A11, A12 and A15, because those are the pins that should be signaling to the 74LS42 to switch the static RAM. So this is pin A10, so that is low. A11 is high. A12, should be A12, is low. And then I have to move so I can see A13 is high, A14 is high, and A15 is high. So we'll check we see those signals coming through to the appropriate places. Now we're seeing activity on the various of the digital pins. I'm not going to test them individually. And then we'll take a quick look at the reset pin, which is pin 40. This should be high. If it was low, then the CPU would be held in reset. So far, this all looks normal to me. So now I'm going to move on through the circuit to the 74LS42. So pin 15 is the least significant bit going into the LS42. That is low. So if that is pulled high, then essentially this device is being switched out and anything connected to it is being switched out, and instead the CPU is trying to access one of the ROMs. Nope, other way around. So this is the least significant bit. So this is A10, pin 15. So this is the least significant bit. So this is not selected. Then A11 is high. A12 is low. And A15 is high. So right now, I think that the RAM is being switched out so that the drive can access the ROMs. I'm just going to reset the drive and see how this changes. So I've turned the drive off. So it just immediately goes high and doesn't change. Now I'm going to take a look at the outputs on this chip. So again, if we look at the pins, so pin 15 is low, 14 is high, 13 is low, no, high. Try that again. So that's pin 15. That should be pin 14, high, 13, high. Right, so we should be seeing all of the outputs of this chip being high. We only care about 1, 2, 6, and 7. So they're all high. Right, I've pulled the second ROM chip out and the other 6502 out, and I'll power the drive back on. So now I'm just getting a solid light from the disk drive, which suggests that the CPU isn't booting at all. We'll take a look at ready. Ready is high. Reset is high. So that's all good. I'm going to reintroduce the second ROM chip. Turn it back on. We've still got solid LED from the disk drive now. I've tried pulling top ROM out as well. Okay, new plan is I'm going to test the main ICs from my 2031 in this 1541. This is my Jiffy DOS 1541, as you can see. It's currently booting. It's booted fine, and it has its original chips in it. So now I'm going to try the chips from the 2031 one by one. I shall start with the 6502. So a 6502, and let's not replace the ROM chip. Not booting at all, which we'd probably expect without a ROM chip. Put the ROM back in. Booting. So that 6502 is good. Now I'm going to swap the two ROMs over, and I'm going to do it as a pair. The reason I'm doing it as a pair is because it won't boot successfully if I only put one of the two ROMs in, because the firmware for the disk drive will be mismatched. It will have half 1541 firmware and half 2031 firmware. Okay, turn it on. Not booting. Now, possible it's not getting the responses it's expecting from the 6522s. Or it's possible that one of my ROM chips has indeed gone bad. Maybe my top ROM has gone bad. At this point, what I'm tempted to do is actually now replace the ROMs in my 2031. So put the chips that came from the 2031 back in the 2031, and try it with stock 1541 ROMs. Sadly, I can't use the ROMs from this disk drive because, as you can see, they're actually attached, at least the upper one is attached to the circuit board for the Jiffy DOS to regular DOS switching. Of course, it's occurred to me that I should really just check these ROMs in the Jiffy DOS drive before I go any further. So I shall do that. So to recap, this is my 1541, and I've just replaced the ROMs with other 1541 ROMs, which I want to put in my 2031, but I'm testing them in this drive just to make sure they work. They do work. The disk drive has booted successfully. So now I'll take these ROMs out and I'll put them in my 2031. But my 2031 is no longer a 2031, it's a 1541, because I've removed the daughter board with the IEEE 488 circuitry, and I'm replacing the 2031 ROMs with these 1541 ROMs. Welcome, Mr. 2031, it's now 1541. Do you boot? No. We're still getting the single flash code. So why we weren't getting that with the, why we'd stopped getting that with the 2031 ROMs, I can't explain. I was still getting a flash code with the first 6522 removed. With the bottom 6522 removed, we're just getting the drive failing to boot. So clearly it needs that second 6522 to be present in order to boot. Right, we're back to the flash code. Now let's put my 2031 ROMs back. Failing to boot. Do I have the ROMs the wrong way around? I don't think so. Still fails to boot. Well, I'm stumped. I don't know why this drive will no longer boot with my 2031 ROMs, whereas I was getting a flash code before. So I thought I should just finish swapping the chips over. So I hadn't tried the 6522s from the 2031 in this disk drive. So I'm just going to do that now. Yeah, and the disk drive boots just fine. Now I don't actually have the 6502 from that disk drive in here, but I do have the ROM chips I'm going to use in there in the 6522s. So, but I've tested the 6502 already in this disk drive and it worked just fine. So let's recap where we are. We started off with a problem where the drive was giving me a single flash code. Now with the 2031 ROMs in that drive, I don't even get that. The drive just fails, the CPU just fails to boot. The ready LED just stays on permanently. I don't know why that's happened. I'm going to treat that as a secondary issue. Coming into this, the first thing I thought the CPU would do was test the 0 page. Of course it can't do that because it has to read some code from the ROM to execute it to actually test the 0 page. So the first thing that the drive has to do is read from the top ROM. So it's not unexpected that I'm seeing a lot of activity on that ROM in the 2031 even when it's not working, because the CPU is grabbing code from it. Therefore, I think it still supports the hypothesis that there's something wrong with the part of the circuit that handles the RAM, either the 74LS42 or the static RAM chip itself. I think it's a 2016. I haven't got my glasses on, can't tell. So I've got a couple of ways I could move forward. The first way is I could continue trying to validate that hypothesis with testing. The second is I could socket the 74LS42 and the static RAM chip and try swapping them out with other chips. Now I do think there's actually some value in continuing to do some testing and see if I can actually find a problem with the circuit that feeds the static RAM, because it's not just the 74LS42 and the 2016 on that circuit. There's also, I think, a 74LS00 and maybe another chip on that circuit, which I would like to check are operating correctly. I mean, the 74LS00 is just that's a NAND chip, and then I think there's an inverter on the signal as well, and they're relatively easy to test because there's simple truth tables for both of those chips. I think that's what I'll do next. I'll use the oscilloscope to probe the circuitry between the 74LS42 and the static RAM chip. So we'll start on the static RAM chip, pin 18, so 13, 14, 15, 16, 17, I'm guessing that's pin 18. Now I thought I saw some activity there for a second. Maybe I was looking at that pin. That's pin 17. I can't immediately see what pin that is. But 18 is just high, so not being activated. So this 74LS04 here goes directly to the chip select line on the static RAM chip. So pin 10 goes out to the static RAM chip. It's a 14 pin chip, so I want that pin. So that is always high as well. Now the input to that is pin 11, which is steady low. Okay, so that chip looks like it's doing the right thing. It's turning a low into a high. So pin 11 on this chip comes from pin 11 on the chip above it. So 8, 9, 10, 11. So low. Alright, brilliant. But it's stable low. Let's have a look at the inputs to this. So the inputs to this are 12 and 13. High. Looks stable to me. And high. So it's a NAND gate, a not AND. So they're both high, so the output should be high inverted to low. So that's doing the right thing. So we're seeing the right output from this based on the output from the LS42. Now the only thing I can think of is that we're not seeing the static RAM being selected at all. So remember, we were looking at pins. If we look at pin 15, 14, 13 and 12, 15 is that one, 14, 13 and 12. 12 is always high. That's going to cause this decimal decoder never to activate any of the outputs that we're interested in. So the static RAM is never being selected. So the only reason I could think that would be is if there's something on the bus that's pulling A15 high that isn't the CPU. Remember, we've tested the CPU in another drive and it works just fine, so it's not the CPU that's at fault. The only other thing that it can be, my conclusion is this 74LS42. So I'm going to remove this 74LS42, stick a socket in there and try replacement 74LS42. I've gone ahead and socketed the 74LS42 and I pulled it out and I checked it in my logic chip tester and it tested fine. I replaced it anyway, no dice. Still the same symptoms from the disk drive. So in a desperate attempt for it not to be the static RAM chip, I also replaced the 74LS00 and 04 chips here. Well, I socketed them, I pulled them out, I tested them in the chip tester and they were fine as well. So finally I pulled out the 2016 static RAM chip and replaced it with a static RAM chip from another of my 1541s. This is a slightly different part, an MB8128, but they're both 2 kilobyte static RAM chips.
and they are interchangeable. And I turn the disk drive on. So we hear the motor spin and then it stops. So it's booted successfully. Similarly, the light comes on briefly and then goes out and stays out. So I think this disk drive is now fixed. I'm going to have to buy some replacement 2016 static RAM chips, or MB8128s, because I don't carry the stock of these. But next thing I'm going to do is replace the IEEE 488 daughter board, make sure the disk drive still boots with that installed, and then just double check I can talk to it from one of my computers. What's this? The disk drive's still in pieces in front of me. Well, I remembered after I tried to get this disk drive to work with my pet that I had to replace the ROMs. You will recall that I still had the 1541 ROMs in this disk drive. So I replaced the ROMs and the disk drive didn't work. Again, you may remember earlier on, I did find that with these ROMs, the disk drive had gone even further backwards in terms of working while I was working on it. So in terms of what these ROMs are, get this under the camera. So turn it around. It's an ST micro part, a 39SF010A, which I think is a megabit ROM, and I've got 16 images written on this particular ROM. Anyway, the disk drive was refusing to boot with these ROMs inserted. So I took each of the ROMs and put them into my programming jig and then put them into my programmer, and I couldn't read the ROMs, either of them. I got a bad pin reported from the programmer on each of the two ROMs. So I have touched them both up using my soldering iron, and it now boots. If I reinsert the top ROM and get it in the right place in the socket and not one pin offset, booted. So that's really bizarre. I don't really understand why both of these two failed. I mean, perhaps my soldering job originally on these ROMs was pretty marginal. In terms of the footprint that TSOP part is connected to, I haven't quite laid it out properly, so it's a bit of a stretch to get from the pins to the pads. So maybe a joint broke on each of the two ROMs because the system had got too hot. Or when I moved the ROMs, probably more likely at that point the solder joint cracked, no longer made contact, so the disk drive couldn't read the ROMs. So there you go. Disk drive is now booting with the correct ROMs installed, so I should now be able to test out its IEEE 488 function. So I've figured out why these ROMs failed. Take a look at the design of the board. I have the TSOP right at this edge of the breakout board. When I turn it over, insert it like that, when I get my tool underneath to lever the chip out, it damages the connections, the pins on the circuit board. And I obviously did that to both of the ROM chips when I removed them to insert the 1541 chips. So I'm glad I figured out what went wrong with these, and I'll have to make sure I don't use this tool to remove these ROMs in future. Fortunately, given their design, you can actually pull them out reasonably straightforwardly with just your fingers. It passed! The performance test actually succeeded on this disk drive. So I'm gonna back away slowly and just cross my fingers and hope that it doesn't stop working like tomorrow. That was a lot more painful than is probably going to come across in this video, assuming I can edit it into something sensible. I went round and round in circles, backwards and forwards. I'm surrounded by dismantled 1541s, swapping parts in and out to try and figure out what all the problems I was seeing were. But as I say, it passed the performance test on the pet. I hope you enjoyed that more than I did. If you did, please stick around and join me for the next episode. Until then, rock on.